Now we're going to discuss about exponential and other functions as mathematical models. Let's introduce the exponential function first. So the general form of exponential function will be y equals a times b to the x power, okay, where the x is the independent variable and the y is the dependent variable, and there is one general or common keywords that we need to know whether it is an exponential function or not. If there is a mention or there is indicated that y varies exponentially with x, so it is necessary for us to know that the y varies exponentially, not quadratically or linearly, but exponentially. So the next one is the a. A is a constant, so in your function, of course, you have to find what is the numbers that can replace a, and usually the a will refers to the y-intercept. So the y-intercept will be a. Why? Because y-intercept is the value of y when x equals 0. And you can imagine that if the x equals 0, then the whole thing in this power will be 1. 1 times a equals y. That's why the y-intercept will be a. And not just only give you a hint about the y-intercept, a also give you a hint about the graph itself. Will the graph be above x-axis or below x-axis? Okay, we will go to that later. So now, what is about the b? The b is the positive constant. So there is a difference between a and b. For a, it can be negative, it can be positive. But for b, okay, let's have an agreement that it has to be positive. Okay, the base of this power has to be positive. And the b constant usually explain or give you a hint about your graph, whether it will gradually increasing or decreasing. So it will indicate the trend of your graph. Okay. Now let's see the graph itself. Okay. For example, now we will have a graph that has a positive and the b is greater than 1. Okay, so there are three different graphs: the purple one, the red one, and the green one. Okay, as you can see here, the purple one is a function of y equals 7 to the x power. So if you refer to the general form, in this function of the purple one, the a is 1 because there is no a, right? 1. So the a is 1 and the b is 7. So because the a is positive and the b is greater than 1, this is your graph. And you can see that the y-intercept is 1. And for the red one here, it is y equals 4 to the x power. And the green one is y equals 2 to the x power. See, the purple one has the highest value of b, 7. And when it is decreasing into 4, the b, look at the difference of the graph. Okay, and the green one, the b is 2. So yeah, you can get a hint about the effect of how if you increase the value of the b or if you decrease the value of the b. But for this one, keep in mind that the base must be greater than 1. So what if the b is not greater than 1, but it is between 0 and 1? For example, 1/3, okay, 1/4. So this is the graph will be. So it will be decreasing. So previously, when the b greater than 1, it will be increasing the trend from left to right. And don't forget that because the a is greater than 0, which is positive, the a constant, so your graph will be above of x-axis. So this one will never cross the x-axis. If you remember about the asymptote line, okay, so don't forget we have a horizontal asymptote, which is the x-axis. It means this graph will gradually getting closer to the x-axis but never touch. Okay, that's the asymptote. So the graph itself, the whole thing, if we extend to the extreme values to the left and to the right, there will always the graph is always be above the x-axis. And that's also the same with the second example. Since the a is still positive, the graph itself will be above the x-axis. But the difference is the value of the b is less than 1. Okay, so it is this is 0.5, this is 0.8, this is 0.2. See the difference? And you can see that the a is 1, therefore the y-intercept is 1 also. And it is decreasing, and again the asymptote, the horizontal asymptote is the x-axis. Therefore, the graph itself is getting closer and closer to the x-axis but never touch. And the whole graph will be above the x-axis. So now how about the next one? So now there are three different graphs here, although it's not as complete as I want. So the first graph is this one, the red one. So this one has the a positive. Therefore the graph is above the x-axis. But the b is less than 1. You can see that this is 2 actually, but actually it's not 2. Don't forget that it's 2 to the power of negative x. So actually it is 2 to the power of negative 1. So it is half. So it is the b is 0.5 here. Okay. When the b is less than 1, so the graph itself will be gradually decreasing and it's getting closer to the x-axis but never touch. But as for the purple one, since the a is still positive, it is 1, so it's still above the x-axis, but because the b is greater than 1, which is 2, therefore the graph itself exponentially increasing. But if you go to extreme left to the minus value of your x, it's getting closer to the x-axis but never touch. Now, the blue one, the a is negative 1. The a is negative 1, but the b is greater than 1. So the a is negative 1. I'm sorry, it's being simplified, but if you can extract the negative, actually this equation will be y equals negative 1 times 2 to the x power. So the a is negative 1, the b is 2. So whenever you have the a is negative, your graph will be below the x-axis. And if the b is greater than 1, so it's gradually decreasing. So actually the point of b positive is your graph whenever the x we go to the greater value of the x, your graph will getting further from the x-axis. Okay, so just compare the purple one and the blue one. Both graph of the purple one and the blue one has the value of b greater than 1. See, when we are going further to the greater value of x, to the positive side, the graph is getting further. It's like that they are avoiding the x-axis, right? And it's the same with the blue one. The b is greater than 1, but the a is negative, therefore it is below the x-axis. And the trend of the graph, they are like avoiding the x-axis when we move forward to the positive x. So you can get a hint that if the a is negative, okay, so it is below the x-axis, But if the b is less than 1, so the graph itself will gradually getting closer to the x-axis, but on below the x-axis, right? So when we move forward, so let me just show you the graph. It's more like this. When we go to the right, when the x is increasing to the positive value, is greater and greater, the graph itself is getting closer. They are approaching the x-axis. Okay, so yeah, that is the trend of the graph. So if we can conclude, this is the general shapes of the exponential functions graph. So if the function is a times b to the x power, if the a is positive and the b is greater than 1, so this will be the graph looks like. And if the a positive, but the b is between 0 and 1, this will be the graph look like. Okay, and so on. If the a is negative and the b is greater than 1, so the graph itself will be below the x-axis, but when we move to the positive x, the graph will getting further from the x-axis. And this one is a negative and the b is lesser than 1, but it's still positive, so it's like 1/3, 0.5, 0.6. Now this is the trend of your graph. So that is about the graph. Now let's speak about the inverse function of exponential. Now I just want to explain you briefly about logarithm function as the inverse of exponential function. Okay, why? Because later I will explain you why we need to learn about this. So if I just recall back the exponential function's general form, and this is the general form, y equals a times b to the x power. So if we're speaking about the inverse, it means we try to change the statement. Previously, y in the so y in terms of x, or y as a function of x. But the inverse means we change the statement into x in terms of y, or x as a function of y. Okay, let me just as x as a function of y. So how do we change the statement here? So let's just copy the original one. So from previously y as a function of x, now let's change it into x as a function of y. So how do we do that? First, let's just divide both sides by a. If I divide both sides by a, so I have the statement becomes y over a equals b to the x power. Right? So how if by what that we can change the statement into x equals what? So we need to use logarithm, right? The logarithm. So use the definitions of the logarithm. Therefore, we can find that x equals log to the base b of y over a. So yeah, that is the inverse function of y equals a times b to the x power, which is the inverse one is x equals this. So why we need to know this? Because of course later in the real world problem, after you have found the equation here, there will be questions. If you are given a specific y, okay, you have to find what is the value of the x, right? Because if you are given the value of the x, it will be easy for you to find the value of y. Just substitute the x, right? Substitute the x and then you can find the y. But if you are given the value of y and you have to find the value of x, you need to use the inverse technique, right? So you need to know that the x need logarithm. Okay, so just to know how about the logarithm graph itself. So it's just for your information. So the blue one is the exponential function, fx or y equals 2 to the x power. So this is the graph. So if, as you recall, the a is 1. It is 1 times 2 to the x power, right? 1 is the A, therefore the y-intercept is 1, and therefore the graph itself is above the x-axis. But because the B is 2, which is greater than 1, therefore the graph itself has an increasing trend, okay? And whenever you go to the x value, positive direction, the y value will increasing greatly, exponentially, okay? And it will be moved avoiding the x-axis. And this one is the asymptote. I just want to recall that back. But the graph of the inverse, which is, let me just say that this one is y equals log to the base b of x over a. This is the inverse. So the logarithm graph is like this. It's like the shadow. If you put the mirror here, the mirror is y equals x. This is the mirror, y equals x. So if you use the mirror, this is the shadow of the exponential. Now this is the inverse function of the exponential function. Just to introduce you about the behavior of an inverse function. So now let's go to the real problem, and I will give you one example from the textbook. So let's do it. I take from the textbook page 303, number 1, population problem. So assume that the populations of the United States is increasing exponentially with time. So actually the first statement has already given you many informations. First, the independent variable is the time, okay, and dependent variable is the population, because the populations increasing exponentially with time. So populations as a function of time. And then we know that it is increasing exponentially. Increasing means therefore the B must be positive, and exponentially it means we are speaking about exponential function, not quadratic function, not linear function. Okay, so there is a lot of hints here. Now the next sentence give you the pairs as usual. We need the pairs. So if we say that 1970 census showed that the populations was about 203 million, and 1980 showed that the population had grown about 226 million. So let me just show you how we find the equation. Since we know it is exponential function, it is increasing exponentially, therefore let's recall the general form of exponential function. Y equals a times b to the x power. So to fulfill or to complete the general form here, to complete the function, we need to find the value of a and b, because they are not variables, they are constants. The variables is only x and y, right? So the objective is now finding the value of a and b to figure out the function. So let's state first the independent and dependent variable. So what is the independent variable? So it is time, right? So based on this, okay, now I will show you there is a problem if we use the time in year. Okay, let's just assume that this is right. So if the independent variable is year and the dependent variable is the population, but let me just use in million, because of course you just need to save the space. Just let's use the unit in million. Therefore, I can see that the non-pairs, we have been given two non-pairs, right? Which is the first pair is the year 1970, comma 203. Okay, this is the population. So of course you know that non-pairs must begins with the independent, comma dependent. So the second non-pair is 1980, comma 226. So when we have the non-pairs, try to replace that to the general form, since we know that this is the x and this is the y, and this is the second x, this is the second y. So if we use the first pair, we have the statement becomes 203 equals a times b to the that power, that big power, right? that big exponent. So if we use the second pair, this is the second equation. Now, based on these two equations, can you find A and B? Of course you can. Since in finding two variables, we need at least two different equations. So actually, yes, we can. But it is not suggested. It's kind of more complicated. So let us make it less complicated. How? Let's revise the independent and dependent variable. Let me show you how it works. So let us revise the independent variable, which is, I'm not using year. Instead, I'm using number of years that have elapsed since 1970. Okay, see the difference? So, and the dependent variables, I still use USA population in million because I cannot, I cannot revise that. So, what is the implication? Because I change it into a number of years that have elapsed. The first pair, because it is 1970, it will be 0, right? Because 1970 means it is 0 year that have elapsed since 1970, right? We counted the difference from 1970. So the non-pairs, the first non-pairs becomes 0, 203. And the second pair, okay, it will be 10 years, right? The difference between 1980 and 1970 is 10 years. So it will be 10, 226. So based on these new non-pairs, we have different approach. So if I change that, so the first function will be like this, and this one will be like this. Now, this is more interesting and more easier for us. Why? Because let's go to the first pair first. If I go to the first pair, it means I will have that the A will be equal to 203 directly. Why? Because we know that when the B to the 0 power is 1, B to the 0 power is 1, 1 times A equals 203. It means A equals 203. So we have already had the A. Because we had already had the A, therefore we just need to substitute A by 203. Let's divide both sides by 203. And here you go. And I really suggest you, no, I just want you not to calculate that by your calculator to find 226 divided by 203. No, don't do that. Since when you use your calculator and then you find that it is an endless decimals and then you put it into the nearest thousands, so you have already given an approximated values in the middle of the steps. No, don't do that. Try to do the approximation for your final answer only. Okay, so let's just leave there 226 over 203. So how to find B? Of course, we know the technique that we try to isolate B by eliminating this 10. So let's raise both members to the power of 1/10, right? So yeah, we raise both members to the 1/10 power. So it will be cancelled. So in the end, we find the value of B. Now we can approximate. Using your calculator, try to approximate it to the nearest thousands. So just make an approximation in the final answer, not in the middle. Okay. So yeah, since we have already found the value of A, the value of B, therefore we have the complete statement of your function where y equals 203 multiplied by 1.011 to the x power. Remember, you have to stick with the definitions of the independent variable and dependent variable since it matters. So the independent variables is the number, or the x is the number of years counted from 1970, and the y is in million. So let's see how that applicates. Now, for example, the question, use your equation, this equation, to predict the population this year. For example, this year is 2021, right? So if we know that y is function of x, so y is fx, so actually the questions can be shortened into what is the value of f of to 2021, right? So the trick part is if you don't stick with your independent and dependent variables, you use 2021 to replace x, which is wrong, right? We know that the x or the independent variables is the number of years that have elapsed since 1970. Therefore, we need to find first the value of x. Okay, let's recall back the function here. Okay, this is our function, and we need to substitute x by 2021 subtracted by 1970. Yes, because x is the number of years elapsed from 1970. Therefore, the x is 51, not 2021. This is the importance of your definition independent and dependent variables. So let's substitute 51, replace x by 51, and by your calculators, of course, let's just put it into the nearest thousandth. Okay, so the final answer is 354.654. And don't forget, let's stick with the description of dependent variable USA population in million. Therefore, don't forget, the conclusion is based on the model, USA population this year, based on the model, approximately 354.654 million. Okay, so based on the model, so it doesn't necessarily the fact, but if the model is correct, of course, the approximations has a little deviations with the current actual numbers of USA population. So now let's get to the next question. Predict the year in which the population will reach 400 million. So you are given the y. Okay, the y is for, so since it is 400 million, we know that the y is in million. So since the y is in million, so let's just replace y by 400. So let's recall back the function again. And we are given the y, so let's just put the y 400. And then how to find the x? Now this is the explanations of inverse function comes to play. So let's find the x by first divide both sides by 203, right? And then we have this exponential statement, so we can use the definition of logarithm to find the x. So x will be equals to log to the base of 1.011 of this whole thing. Remember again, do not calculate this value in the middle and try to approximate. No, just leave it like that. And then use your calculator to calculate the whole thing this. And then we can approximate the last numbers, the last answer. So the answer, if I'm using my calculator, the answer is 61.998 and so on. Don't forget, the x means the number of years that have elapsed since 1970. So you have to know what you are doing. So what are the answers referring to? It doesn't necessarily that this is, so you just cannot say that, okay, the population will reach 400 million in year 61.9. No, it's not, right? Because 61.998 is the number of years counted from 1970. So we just add 1970 by 61.998. The conclusion is, yeah, the population will reach 400 million around year 2031 or 2032. So that's how you use the model. That's how you use the functions of exponential. Uh, yeah, so be careful with the statement of your independent and dependent. Remember, we try to use the definitions to make one value of x, one non-pair, become zero. That is the the foundations of not the foundations. That is the best technique that you can do. Why? Because if we have the one pair with the value of x equals 0, it will be easier for us to find the a. And then we can easily find the b also, and then we can answer the questions. But don't forget, whenever you answer the questions, you need to refer back to your definitions of independent and dependent variables. So for example, I changed the independent variables and the independent variables. Okay, so let me just number of 10 years that have elapsed. Okay, so can I change it? Yeah, of course. I want to make it simpler. So let me say that this number of 10 years that have elapsed since 1970. If I change that definitions, my non-pairs will be, look at again, assume it is 1970, the number of population is this, and 1980, the number of population is this. So my first pair will be the same since it is counted 10 per 10 years from 1970, so it is 0. But the second pair will be changed, right? It will be 1. Okay, because 1980 is 10 years from 1970. So it will be much simpler. So the first pair is the same. The second pair will be 1, comma 226. So it is b to the first power. Wow. So actually we have to skip this one. In the end, we just know that b will be equal to this one. So let me use my calculator to find it. So 1.1133. So of course I need to use the approximations because it's not exactly. Okay, so yeah, we almost, but look at this. This is kind of different. Mister, is it safe? It's different function. Well, of course it will be different, the function. That's okay. But as long as you are consistent with it. So because the b is 1.1133, so let's just change it. 1133. Remember, we have new functions. Why? Because we changed the definitions of the independent and dependent variables. Okay, so let me just you answer the next questions. Use your equation to predict the population this year. So 2021. Therefore, we know that since it is per 10 year, I need to revise this, right? So it's just not 51. 2021 is 51 years after 70. But if we use per 10 years, so let's divide by, let me see the division, by 10. So actually the x becomes 5.1, right? 5.1, and we need to revise the equation, and then yeah, and this is the equation 1.1133 to the power of 1.1, 5.1. Okay, so let's see, do we have the same result? 203 multiplied by 1.1133 to the power of 5.1. So yeah, it's a little bit, yeah, it's different because of course we are playing with exponential and we're playing with approximation, but it's still acceptable. So the result is 350.928. Okay, so based on the model, if I revise the definitions, yeah, we slightly different, but not that, yeah, that big. So it is still acceptable. Therefore, if you are asking me, Mister, which one is the correct one? As long as you are stick with your, consistent with your definitions, with your function and how you answer the questions, it's fine. It's fine. So based on the model, so that's why we need to be clear based on my model, okay, based on the new definition, based on the new function, the USA population this year approximately will be 350.528. That's how you say it. Okay. So now let's answer the next question. Predict the year in which the population will reach 400 million. So I will use the new function based on the new definition, right? So still about the y, there's no change. So it is 400, and this one is 1.1133. Okay, so yeah, I just use the same technique. So the rest will be the same. We are just changing the b, right? So the last one will be like this, 1.1133. Okay, and let me count the result by using my calculator. So it will be log the base of that to that. Let me just divide by log 1.1133 log 1.1133. So it is 6,3194. Let me just use. Okay. So do we have a different one? But actually, no. It is 10 years from, don't forget. So actually, to find the exact numbers of what year of 400, it will be 1970 plus the answer of this one, 6.31, and so on, multiplied. Don't forget, because this is per 10 years, it means you need to multiply it by 10. So in the end, we have around to 2033. So yeah, it's the same, almost the same. Before we approximately have year 2032, 2031. Yeah, a slight different 1 year. so so the difference, why there is a difference, because we use approximation. When you use approximation, remember when we find the function here, when we find the b, we have already had approximation. So when we change the value, approximations is not the exact value. We change it. Therefore, there will be difference. But that's okay. Again, that's why I'm expecting a slight different answers from your part. That's fine. But I just want to see how do you find that, how do you determine the definition here, and then how do you find the equation, and then how do you find the answers. That's the key point. So good luck with the real problem. I hope by these explanations you can do your homework well and you can practice.